Hello, this video is about connected particles, and it's going to go through a problem of two particles connected by a pulley where one is on a table and a horizontal table and the other one is hanging vertically. So the situation looks like this. We've got this mass here, this M1, and we've got the M2 here. We have a pulley on the edge of this table. So M1 is on the table, and then we have a string which is connected to M1, and it passes over the pulley and connected to M2. So M1 and M2 are connected by that string. M2 can move down, and M1 can move along the table. Okay, so I'm going to go through example 14, which is on page 174 of the Year 1 Mechanics and Statistics book, and that is in the chapter 10, Forces and Motion chapter. Okay, so here is the problem. Two particles, A and B, of masses 0.4 kilograms and 0.8 kilograms respectively, are connected by a light, inextensible string. Particle A lies on a rough horizontal table 4.5 meters from a small smooth pulley which is fixed at the edge of the table. String passes over the pulley and B hangs freely with the string taut 0.5 meters above the horizontal ground. A frictional force of magnitude 0.08 g opposes the motion of particle A. The system is released from rest. Find the acceleration of the system, the time taken for B to reach the ground, and the total distance travelled by A before it comes to rest. So, what we have then is a situation where it's released from rest. The system is released from rest. B, which is this M2, will travel to the ground. We've got to, well, first of all, we've got to calculate the acceleration of the system. We've got to calculate the time taken before this M2 or B comes to rest. And then A will be travelling, which is BM1, along the table. And then we've also got to find the distance that A travels before it comes to rest. Now, what will happen with A, and A is M1, is that it will travel with the same acceleration and the same speed as the M2 until it reaches the ground, until M2 reaches the ground. And then at that point, A will still be moving. The M1 will still be moving. So it will move, but the string will have become slack. So the forces on A, or M1, will have changed, and it will travel just with just the friction force will be acting upon it, and it eventually come to rest. And we have got to calculate the total distance travelled before it comes to rest. Right. So the first thing to do, like it is in any of these problems, is to draw a diagram. So the diagram, will look like this. We have the table. We have A and on the table and B there. We have the pulley here. And we have the distances. B is 0.5 meters above the ground, and A is 4.5 meters from the pulley. Now the next thing to do, we have to put on the forces acting on each particle. So doing that, we know that, well, each one has weight. Let's do A first. The mass of A is 0.4, so the weight of A will be 0.4 g. and opposing that, of course, is a reaction, R. There is a friction force acting on A because it's a rough table, which is 0.08 G. So A will move to the right, and so the friction force is to the left, 0.08 G. And of course there is a tension in the string T. For B, and these are going to be in blue because they are blue forces are going to be acting on B, red forces are going to be acting on A. B is 0.8 kilograms, so the weight is 0.8 G, and we just have the tension in the string. Now the acceleration, because it's an inextensible string, the acceleration of each particle is the same, and we'll call that A. For A, particle A, the acceleration is horizontal. For particle B, the acceleration is vertical. So they're not so the magnitudes of the acceleration are equal, but the acceleration itself is not, because they are different directions. Remember, acceleration is a vector quantity, so it has both magnitude and direction. Okay, so that is the diagram. Okay, so the next task is to find the acceleration of the system, that is A. And of course what we do is we use Newton's second law, what we normally do, and we're going to do that for each particle. This time we can't, it's not like two particles that are travelling both horizontally where we can consider the whole system. Because the particles are not travelling in the same direction, we can't do that. Yeah, they have the same magnitude of the acceleration, but not the same direction. So we do have to consider both particles separately. So let's go for A first of all, horizontally. So for A, resolving horizontally, which we write like that, we have T minus 0.08 G equals M, which is 0.4 A. And then for B, resolving vertically, and we'll go down in the direction of the acceleration, we'll have minus T plus 0.8 G equals M, which is 0.8 A. So two equations in A and T, 1 and 2, and then we will solve those simultaneously for A. So we eliminate T, we can just add up the two equations, 1 and 2. T will be eliminated, it will cancel, so we have 0.8 G minus 0.08 G, so that would be 0.72 G equals 0.8 and 1.4, so that's 1.2 A. So A is equal to 0.72 G over 1.2, which is going to be 72 over 120, 6 over 10. I think it's 3 G over 5. Meters per second per second. Now, we found the acceleration of the system, so we can now, we know the acceleration is a constant, so now we can look at the motion of A and B. Well, the first, the next task is to find the time taken for B to reach the ground. So this is just motion under constant acceleration. We can use the Suvat equations. If I write down Suvat, we can see what values we have. Now B is going to move 0.5 meters vertically down, so displacement 0.5 down. So that's the direction. It starts from rest, so u is 0. We don't know the velocity when it hits the ground. A is, of course, well, what we just found, 3g over 5. And t is what we've got to find. So we need to use the equation that doesn't have v in it, which of course is s equals ut plus a half at squared. Substituting the values, 0.5 equals 0 plus a half times 3g over 5 t squared. Which means that if we substitute g as 9.8, we'll have that'd be 5 times 9.8 over 3 equals t squared. So it gives t squared would be 5 over 3 times 9.8, substituting g as 9.8, which is 25 over 49 times 3. Work that out. 9.8 is 49 over 5. And then we can take the square root, we get 5 root 3 over 21. So that's the time taken. Now, the next bit is the total distance travelled by A before it first comes to rest. Now, you've got to appreciate that at that point, the forces on A change because the T disappears because the string will go slack. So, we've got to consider what happens after that. Well, we need to know what the value of the velocity is at that point. So we need this v here. The velocity of A and the velocity of B, or the speed of A and the speed of B will be the same. The velocity, of course, will be different directions. So finding the velocity using v squared equals u squared plus 2as, we will have v squared equals 0 plus 2 times 3g over 5 times 0.5. That will give 3g over 5, since 2 times a half is 1. G is 9.8. 9.8 is 49 over 5, so that will make 49 over 5 times 5, 25. So v itself is the square root of that, 7 over 5 root 3 meters per second. Right, at this point, I'm going to finish this video, so I can only make 15-minute videos maximum, and I will continue this on the next video. So I'll see you in a minute on the next video. Thank you.